Hello and welcome. Today we're going to talk about inverse trigonometric functions. And again, this is going to be a lot of just definitions and a little bit of analysis on what it is to be an inverse trigonometric function in the complex plane. So, for instance, we have something like this. We had sine x equals y, and over a restricted domain, we could write this as sine inverse of y is equal to x. And these functions were very standard. We knew their derivatives and everything. So now we're going to expand how and see if we can derive a formula in the complex plane. So again, what we want is some w is equal to sine inverse of z. Okay, so we can write this in a different way. We can also write this then as sine w is equal to z. Okay, so with this form, I'm going to rewrite this as e to the I w minus e to the negative I w all over 2I is equal to z, because that's simply the definition of the complex sine function. All right, and then what we want to do then is solve for w. Okay, so let's do that. How do we solve it? Well, we're just going to start doing our best. E to the I omega minus e to the negative I. No, those aren't omegas. Those are w's. I'm sorry. Is equal to 2iz. Okay. Next thing I'm going to do now is multiply everything in this equation by e to the I w. Okay, and that makes e to the I w quantity squared minus 1. And then I'm going to move this over, and then that's going to be equal to 2iz e to the I w. All right, I'm going to just rearrange this equation a bit. We have an e to the I w quantity squared minus 2iz e to the I w. I'm going to put that in a little parenthesis again there. Minus 1 equals 0. All right, so this looks like a quadratic. In e to the I w. So let's see if we can solve for e to the I w. So the quadratic equation, it turns out, works every bit as fine in the complex plane. And so we're going to do that. E to the I, e to the I w then is equal to, and we have to do this right there, that's our b, and our a there is 1, and this is our c, which is equal to negative 1. So as you are well aware, we go minus b, so that becomes 2iz, and then we do plus, and I'm going to use the square root of, and this will now be our complex square root. I don't have to write a plus and a minus because the complex square root takes care of both of those at the same time. And that's going to be b squared, which is then negative 2iz quantity squared, minus 4ac. So in that case, it's going to be minus 4 times negative 1 times 1, all over 2a, which is just 2. Okay, so let's see if we can rewrite that. That becomes an iz plus, and we see here there's a common let's multiply it out, and there's a 4, and there's also a 4 here. Those 4's come out and cancel with that 2. So we're left with, and I'm going to do this little calculation down there just to help everyone out. So that becomes a 4. Then I see an I squared, and then I see a z squared. Likewise, I see a plus 4 there. Okay, so that becomes a 4, 1 minus z squared, because that right here is a negative 1. All right. Of course, then the 4 pops out of the square root and gives us it cancels that 2, so we're left with a 1 minus z squared. So that's the formula. All right. So the next thing we have to do then is, so I'm going to have to rewrite this on the next page. So that is e to the I w is equal to iz plus square root of 1 minus z squared. So that's what we had from the previous line. Now, we can always write e to the I w as, this is a complex exponent. We've seen those from previous videos. We can write that as e to the I w times log e, which is simply e to the I w again. But another way to put this is that we can take the complex log of the whole thing and then get out e to the I w. But we just got to remember this is the multi-valued log function is equal to log of iz plus root 1 minus z squared. Okay? And so that means that if I multiply this by negative I, both sides, I get w is equal to negative I times log. This is the multi-valued log function, iz. Remember, this is also a multi-valued function. This gives us both plus or minus. Sorry, that's not multi-valued log. That's multi-valued square root. So that gives us, and also that is multi-valued log as well. So that gives us a way of writing this. Okay, so let's just quickly do an example of how this works. See if so. This now is equal to, that is our definition for sine inverse z. So it, again, is a multi-valued function, and so we always have to keep track of the branch of log that we're interested in, and also the multi-valued nature of square root, because we have those two principal roots that come out of it. Or sorry, there's a principal root and a non-principal root for the square root. There's always two solutions, or two outputs to the function. All right, so let's talk about an example. So let's do it here. So let's try sine inverse of negative I. So here's a good example. Let's see if we can figure this one out. So again, the definition is complex log times negative I times I times z, and z of course is negative I, okay, plus square root of 1 minus negative I quantity squared. Okay, so our z goes in there, All right. That becomes positive 1, and then we have a plus square root, and we have 1, and that so I squared then becomes negative 1. That becomes a positive. That becomes positive 1 right there. All right. So remember, this is multi-valued, so that becomes negative I times log of 1 plus or minus square root of 2. All right. So so now let's recall what this is. So remember, log is continuous with the real natural log for real values, for positive real values at least. So we have to think here. 1 plus square root of 2 is a real number, and it's also greater than 0. In which case, log of 1 plus square root of 2 just reduces to the natural log square root of 2. Okay, so that's good. So okay, one value. So that means that sine inverse negative 1 negative I is equal to negative I times 1 plus root 2. Okay, but there's another value for it, and that's when That's for when we have 1 minus square root of 2. This is less than 0. A real number, but it's less than 0. So we have to write down what that is. 1 minus square root of 2 can be rewritten as uh, 1 as square root of 2 minus 1 e to the I pi. Okay, so that we're going to take our principal value there. All right, so this is one way to write it. All right, so with this representation, then we put that in. So natural log, or sorry, the complex log of root 2 minus 1 e to the I pi becomes root 2, natural log of root 2 minus 1. That's a positive value in there now. Plus I pi. All right, so then now we have here negative I times natural log of root 2 minus 1 plus I pi. We can rewrite that as pi minus I natural log of root 2 minus 1. All right, so those are our that's our multiple valued solution. So we plug in a minus I and we get two answers coming out of it, and we have to choose which one we want to use for particular, whatever our purpose is for inverse trigonometrics. And so we'll learn more about which one we need to choose for various problems in a later date. But the idea here is that we're taking an inverse, and like anytime you have an inverse, if you have some function of z and it goes to some w, and then I want to find out what z could possibly produce that w, and it could be, there could be more than one value. All right, so in general, typically we know that f inverse doesn't exist when there's more than one value, but in some cases we can actually keep track of which inputs. In this case, these are values for that could produce a sine, a particular sine output. All right, so that's why the trigonometric comes in handy, or this inverse trigonometric comes in handy. Okay. So that's a good example here. So now let's talk quickly about the definitions for some of the other trigonometric functions. So, and I'm not going to derive this, but just state that cosine inverse of z is equal to negative I complex log of z plus I 1 minus z squared square rooted. Okay. So again, that's the multi-valued square root. And of course, tangent inverse of z, we can write it as I over 2 log I plus z over I minus z. All right, and you could derive all of these if you wanted to go through the process, but we'll just state them as definitions. And likewise, these functions, of course, log is analytic over its domain once you choose its branch. And then, of course, tangent is analytic over its domain when you choose a branch for log as well. At any rate, because this is an analytic function and this is an analytic function, we can take derivatives. So d of sine inverse dz. It's a standard. It's just like what we've seen before with in your calculus class, and d cosine inverse z dz is equal to minus 1 over 1 minus z squared quantity square root. And likewise, and probably more famously, tangent inverse of z. Tangent inverse tends to get more important. It gets more attention because it's used so often to find angles. Is 1 over 1 plus z squared. Okay, right. So those are the classic results that we get, and they are very standard. They're what we've learned from real variable calculus. So finally, we're just going to talk quickly about hyperbolics, and I'm just going to state some of the identities. Inverse hyperbolic sine can be written as complex log of z plus z squared plus 1 square rooted 1 over to the 1/2, and cosh inverse is equal to complex log of z plus z quantity z squared plus 1 over square to the 1/2 power. Okay, and finally, inverse hyperbolic tangent is equal to 1/2 complex log 1 plus z over 1 minus z. All right, so and of course all of these are also analytic over their domains. And because this is an analytic function composed of another analytic function, we can take derivatives of these, and I'll leave those for exercises. At any rate, now you see that much of your calculus then just transfers over for trigonometrics and hyperbolics to be very straightforward. So thank you very much.